we've got this idea of a magnetic field around a current carrying wire, but we want to approach the idea of a current carrying coil. Current carrying coil has a name. It's called a solenoid. Which sounds kind of fancy and futury, but we've been using solenoids for ages. This is a picture. Well, this is a picture of a solenoid. This is an actual solenoid. You notice that it has what would end up being positive and negative terminal, current going in one end and out the other end. Depending on the resolution of what we can see on the screen right now, each one of these wires, can you see if I touch it with my pen? Maybe I can't disturb the wire, but it basically is like a curly, like a spring. Actually, here's like somebody at some point in the history of the school decided that we needed to spend $100 on a model of a solenoid. It was not me, but there you have it. There's one that has only a few coils. There's one that has a lot of coils. And that no doubt came from the physics catalog of science. But now you can see it. So this is supposed to be like, hey, we can see this if we zoom in on it. And at some point, the soldering's broken on the back of this one. But if you run the current through this one and you put a little tiny compass, which according to the instructions came with the kit, but I can't find the tiny little compass anymore, it really would point in the direction of the magnetic field around that solenoid. Okay, I don't have any tiny little compasses that will even fit inside of this box. But there you go, model of a solenoid. And the soldering is really broken on the back. You can see. I got to take that down to the electronics shop and get that soldered up. Anyway, by following a loop with the right-hand rule, which I'm going to short form down to the RHR. Maybe we should make ourselves a little note, because we might refer to the RHR a few times, the right-hand rule. And there are 3 right-hand rules, and we've only talked about one. But if we talk about the right-hand rule for straight conductors, we can develop a new right-hand rule for the magnetic field. Remember, magnetic field is the B field, produced by a current loop. Called a solenoid. All right, so here's a cross-section of a single loop. And, like a minute ago, I held up a big hula hoop, just like act out holding a solenoid, so we can have like a macroscopic solenoid. But you can picture half of a hula hoop just as easily as anybody. One person said, this looks like a ridiculous macaroni noodle. I guess so. But it's a cross-section of a loop, okay? And I put up the model of the solenoid just a second ago. But this current is traveling through this loop. And just to really emphasize what's going on here, there is an X right here. That means the current's flowing away from us on that side. And there's a dot right here. That means the current's flowing towards us on that side. Remember, we had the current flow conventions for 3-dimensional thinking the other day, where if there's an X, it's like the tail feathers of an arrow flying away from us, like an archery arrow. And the dot is like the tip of the arrow flying towards our face, right? So it's coming towards us. And if I take my right hand, I'll grab the right hand of the Yeti here. You can see that there's a right hand wrapping around that coil there. Can you see how the fingers would be wrapping up inside of the coil and down outside the coil? Can you see what I'm talking about with, not a Yeti, I guess he's a Bigfoot. Yeti's my coffee cup. Bigfoot. It's a totally different character. Anyway. And then on this guy here, same process. Ignore the thumb. We're talking fingers, right? Orienting upwards on the left-hand side. And then if we bring the Yeti around this way, it would be going downwards on that side. The only reason I'm using, not the Yeti, Bigfoot. I'll get myself straight. The only reason I'm using the Bigfoot right now is that I can't get my hand around that little wire. My hand is too enormous to fit around that little wire, right? But you can picture what I'm saying. There you go. That's a good use for having Bigfoot around. All a part of the lore. All right. So if I take this coil and I loop it, what I end up getting is a structure that looks like this, where I got this hand holding on to not just one coil, like the Bigfoot was doing just a second ago, but multiple coils. And these coils actually build up the magnetic field within, so that, look, there's a magnetic field going this way, do that part of the coil, and there's a magnetic field going this way, do that part of the coil, and this way. And actually, all of these magnetic fields are orienting so that they're kind of coming like if you're thinking three-dimensionally about these coils, they're kind of coming out of that coil. What that means is that this front-facing side of the coil, if this is in the back here is the background, and out here where my finger is right now is in the foreground, this coil is facing so that there's a north pointing at us out of the page. And I think that three-dimensional pictures can sometimes be confusing, so I want to try this. I want to take a toilet paper roll. There's my toilet paper roll. I want to send current in the background and wrap it around my toilet paper roll. Toilet paper roll is a good construct because everybody's familiar with the shape of it. And we can definitely picture almost immediately that this is three-dimensional. Whereas the picture on the right-hand side, a picture that commonly shows up in textbooks, it's hard to see the three-dimensionality of a simple line drawing like this. It kind of, in our imaginations, it flattens on a 2D page. So what we're saying is that if the current flows in, this would be the positive terminal, in, it's going to wrap around, it's going to come around into the foreground, it's going to come out to the negative terminal. And you can play around with this. Grab this wire, this line of wire that we just drew with current flowing through it, and grab it in your mind's eye. Like grab these wires in the foreground with your right hand in your imagination. Here, I'll grab the Yeti's hand. But we can see that if this, not Yeti, Bigfoot, if the Bigfoot grabs those wires, you see that the magnetic field would be going down in the foreground in front of those wires, but the magnetic field underneath of those wires would be going upwards. What that means is there would be a magnetic field coming out of this solenoid. Maybe I should color code this so that I don't have wires that are blue and a magnetic field that's also blue. I've got a magnetic field that's coming out of this solenoid such that that would make this solenoid be north at this end and south at this end, because that magnetic field would wrap around external to the solenoid like this, coming back in the other end. And I'm not going to draw all the other field lines. I just want to draw this one field line. You know that the magnetic field around the solenoid would be three-dimensional, right? It would look like that three-dimensional form, that almost donut-like shape. But the magnetic field is kind of firing out of the mouth of the solenoid. I don't know. Does this help it to be more three-dimensional for you? So? All right. All right, let's fill in some more blanks. Let's see. Oh, maybe I should make a little note. It's a donut-shaped field. Donuts. Where the stands for magnets. All right, so solenoid shape, field shape, the current seems to cause the magnetic field to spew, quote unquote, out of the center. Out of center of the coil, so that if we could see these field lines in a 3D, it might look like a donut. And observing the magnetic fields made by electrical current. Let's see. These are three different ways that people represent magnetic fields around an electric current. One's the cross-section method, so 2D cross-section. And with the 2D cross-section, we do have to emphasize that current's going away from us here and coming towards us here. So I'm just going to emphasize that. But using your right-hand rule, you can recognize that the magnetic field would orient this way, below the wire, for current coming towards us. Grab that, actually take your right hand and grab that wire in your imagination. I think I said once before that you can always tell the engineering electromag exam because there's a bunch of smart-looking people grabbing at the air with their right hand, right? That's totally fine. Very normal. So if you're on the test and you whip out your right hand and you start like grabbing at wires, it's not going to look silly. Everyone's going to know what you're doing, okay? Likewise, current going away from us, magnetic field orients as shown here clockwise for current traveling away from us. Another way that people try to do it is with a 3D model or 3D illustration model. Now, this one is one that shows up a lot in computer simulations. People don't typically try to draw these themselves. It's going to end up being the same. I mean, take a look. If the current's going away from you here, follow the arrow on this curve. This is also current that's going into the page here and coming out of the page here. So the magnetic field around this guy is going to be the same shape. The problem with this is that this magnetic field is locked into the page, and to rotate it out into 3 space becomes problematic for drawing, right? But it does kind of illustrate the idea of it being a donut shape anyway. This last one is the loop schematic model. And this is the idea of taking that hula hoop and just lying it flat on the page. Something has to be 3-dimensional because it is 3-dimensional. Current here going in on the positive side, coming out on the negative side. So we have our current flowing around the loop. And as it goes around the loop, I'm going to add in red what the magnetic field is doing. Notice that at any portion of the loop, I should be able to reach around this thing with my right hand. And again, in your imagination, in your mind's eye, or like literally pick up your right hand and try this and wrap it around that wire in your imagination. It's going to be going down in the foreground and up in the background. And what that's going to mean is that single loop has a north-south polarity to it, because it always comes out of the north end in the center and loops back around to the south end at the center. And then there's this idea that's the hybrid model, or I've heard people call it the garden hose model. It's kind of a hybrid of the last two. But it still requires you to be a 3-dimensional drawer. So here we go. This idea of the garden hose. And quite frankly, I don't care which illustration you use. These are all just illustrations to help us be able to picture what's going on. Once you have your positive and your negative terminal for this garden hose, you can add in the current flowing through the hose. And then like we did with the loop schematic model, we can trace around this with our right-hand rule. To talk about what's happening with the magnetic field around it. Anyway, I only bring this up because you're going to see these different kinds of visual models for how to illustrate this stuff. And you got to be able to understand what the heck you're looking at. Anyway, solenoids. These guys are tightly wound wires. When I say tightly wound, I really mean like, see, this is an actual solenoid. If you can even see with the resolution, can you guys see with the resolution that this is really fine wiring? Like, I think the wiring on this one's about as thick as fishing line. Like it's people call it speaker wire. If you ever tear apart a speaker, you'll see the really, really fine wiring inside of a speaker wiring system. And typically you're just looking at these solenoids, and that really fine wire allows you to build up lots and lots of loops, which allows you to magnify the magnetic field, which in a speaker you'd really like to do, because the changing electrical flow and flow rate through this coil is what changes the frequency of the in and out of the speaker diaphragm. Yep. For this guy here?
Like for anyone, like how would you know which way you're supposed to?
How you mean like for the magnetic field? Where, so.
If it's going up in the.
Oh, okay, yeah. How would you like map out what's the magnetic field doing around this wire?
Yeah, because like you said, you can go like up in the foreground and down the back.
Yeah. Okay. So here, I'll zoom out, and I happen to have the bungee cord of physics here. Glad you asked. And on the bungee cord of physics, I've sat down. You see that there's some Sharpie. I've written in Sharpie some arrows. So those arrows are the current flow that's flowing through this wire. Okay, and I can reach my hand around, and my thumb goes in the direction of the current, and my finger's going to curl down in the foreground and will be up in the background. But really, I'm just following that pattern. And if I take this bungee cord and I loop it around, then that's actually what we're illustrating here. I still would be going like this, and it would be, I guess, like down and to the right in the foreground, I feel like. Over here, it would be like up and to the right in the foreground. But oh, my thumb's going the wrong way. My bad. Up and to the left in the foreground, down into to the right in the background.
So you have to say both directions then?
Usually I just talk about what's going on in the foreground.
Okay.
Yeah, but I mean, the nice thing is, like, while I have this out here, and I wish that I'd drawn arrows all the way along it, but I feel like at some point I ran out of steam on drawing arrows on my bungee cord. But you can see, like, as I loop this around, you would have all these arrows pointing like this, and I could reach inside of this bungee cord, and you can see that my thumb is going in the direction of the arrows, and the magnetic field would be going that way inside of the bungee cord, and then looping around that way in the foreground of the bungee cord. And when I go back up here and I look at my toilet paper roll, you guys see that that is the toilet paper roll. Now, the other thing is, it's not quite like this illustration. You notice that this one here, the coil is coming onto the scene in the foreground, or at the top in the foreground, whereas my toilet paper roll, I wrapped it at the top in the background. And so there actually is right-handedness and left-handedness to when we make coil solenoids. You guys see what I'm talking about? If I were to recoil this thing, I could recoil it so that it does enter from the background. And now it's starting to look a little bit more like the one that I have in my illustration, where it's entering from the background and the current is going to the left in the foreground. Are you guys picking up what I'm putting down? Yeah?
How did you know the toilet paper was going from the top?
Oh, so like right now, I've constructed that toilet paper roll basically out of bungee cord. See how the current's going to the left in the foreground? I can take my right hand and I reach inside of that solenoid behind those wires, and the magnetic field is going upwards inside of the solenoid, which means that when it shoots out the top of that solenoid, just like when I look at a bar magnet, the magnetic field that shoots out the top shoots out of the north. That's what we've said before with our conventions for bar magnets. So yeah, that's how you recognize the polarity for your solenoid as well. That's good. That's some good questions. I'm glad that I had all these random pieces of junk on my desk to like answer them. That's why I had the junk on my desk, actually. I don't always get to answer them with all my junk. Anyway, any other questions before we move on? All right. I mean, at the end of the day, we're talking about coils. So I could talk about coil density too, right? Like this is a spring, but if I run electricity through it, it suddenly becomes a solenoid. So I could talk about having coil density. Notice that there's less coils per unit of length there. If I run the same electricity through this solenoid as through this solenoid, the higher coil density is going to make it stronger, which is exactly why we use fine wire, so we can get as many coils as we can in there. That makes sense, right? So coil count is even a thing. That's a thing we actually have to do. And if you buy any one of these things, I don't know if you probably can't even see it on this one, but when you buy one of these solenoids, the manufacturer always tells you the coil count because that's important. All right, so moving on. Current carrying, carrying current. There we go. So the field generated by a solenoid has an orientation. Oh yeah, I can zoom back in again. Yeah. Thanks for asking. As an orientation and an intensity. I guess those had to be ends. And it's made up of field lines. Okay, fine. And there's a second right-hand rule, which is what we're talking about right now. It describes the field of a solenoid. Right-hand rule number 2. So that's actually what's on the next page. Let's take a look at right-hand rule number 2. But right-hand rule number 2 stands on the shoulders of right-hand rule number 1. Because remember, we used right-hand rule number 1 to figure out the polarity of the solenoid. So right-hand rule number 2 for solenoids, the right-hand rule for solenoids requires you to curl or wrap your fingers around the solenoid in the direction of current flow. So we don't have to be reaching inside of the solenoid that we were doing previously. That's just like sort of to build up the pattern of behavior of the magnetic field. Usually a core is placed within a solenoid. And the domains, the reason we have a core is that the domains, remember we talked about domain theory for permanent magnets before, of the core help to reinforce the strength of the electromagnet. So you can imagine if this was my solenoid that's being illustrated here with this hand gripping it, I would talk about the current going up in the foreground and down in the background. See how I'm grabbing it exactly the same way as the hand in the illustration, up in the foreground, down in the background. And then what we're saying is the direction of my thumb is the north pole of that solenoid. That's what that illustration is telling us. And actually, if you go back to the previous page, we can check that. Look, if I take a look at this toilet paper roll that I drew, I take my hand and, uh-oh, did I do this wrong? Well, this is where I have to admit a mistake. My right-hand rule says that if my current is going to the left in the foreground and wrapping around, I should be having my thumb pointing down. Man, I hate when I have to admit a mistake. That makes that be north and that be south. But if we can't admit our mistakes, then, well, that's not good. That means I have to change all these field lines. And I bet you there's somebody that's watching this video at some point that's going to have like some sort of a rage event or something. They're like, no, you did it wrong. We figured it out. Don't worry. Oops, I did it wrong again. What the heck am I doing? Has to go out of the north and back around to the south. All right, at least we fixed ourselves. Do you guys feel like everything's better now? Okay. You didn't notice before? That's okay. I would have noticed it like tomorrow and then been so upset with myself. I'm so glad that got caught. All right. So back to this thing here. Now we got the north end of this solenoid. Again, though, isn't this the 3D model? And this is the thing that I find annoying. So often in our textbooks, we end up getting the 2D model. I cannot tell what's in the foreground and what's in the background on this illustration. Like, I feel like I need to slip a toilet paper roll inside of this thing just to keep track of what's in the foreground and the background, which is why I generally do. Like, I'll redraw these things. If I can even sort out what the illustration is telling me in the first place, I'll redraw it with a toilet paper roll so that I'll declare this guy here to, let's see, how are we going to do this? It's going to have to come in the background, wrap around the foreground, and then go up. So that this is now our illustration that matches. Obviously, I've drawn it with less coils, but current's coming in the background, coming out in the foreground. That means that it's going to be going up in the foreground of the toilet paper roll that we've just inserted in there. And since we've brought in the idea of a core, let's call that a metal core now. It's made of iron. It's not a toilet paper roll anymore at all. It was always just going to be an iron core. Okay? And so now that there's current going around that core, I wrap my fingers around it, and that means that this ends up being, according to the second right-hand rule, the north end of that solenoid, the south end of that solenoid. And now that that solenoid has a north and south polarity, that metal core, remember we said this previously, its domains are going to align with the magnetic field of the solenoid, like a whole bunch of a million, billion, trillion compasses lining up with that solenoid, interior to the solenoid. And the fact that now all the iron inside that iron core is aligning with the magnetic field of the solenoid, this is a permanent magnet inside of an electromagnet. And it makes it stronger. And we can talk to the materials scientists, the metallurgists out there, to figure out what kinds of metals we'd want to put into a core, alloys, whatever, maybe a doped metal of some kind so that the magnetic fields would fade quickly. Can you imagine that that's exactly the kind of thing that you would use at the auto wrecking yard to pick up cars? You'd make an electromagnet like this. The core would be something that strengthens the field quite a lot. The domains would align, but you'd want them to fall out of alignment rather quickly so that you could drop the car. This is a thing, right? All right. So we're going to have this idea that the core makes the solenoid stronger. Core strength. Just ask the CrossFit people. Okay? Core makes the solenoid stronger. The other thing we want to point out is that whether we're talking about a magnetic field or a solenoid, it's the same magnetic field, a permanent magnet or a solenoid, same magnetic field shape. Orients out of the north and into the south. Okay, so here's our hand-drawn version. Here's the professional textbook version of the three-dimensional core. With the professional textbook version, oftentimes what they're going to include is a switch and a power source. Now, the long line of an electrical power source for a DC source is the positive terminal. The short line is the negative terminal. The textbook won't typically put in the positive or the negative. I'm adding them in right now. You need to know that. That's something you need to know for an evaluation, okay? Or just reading any schematic, that the long end, the long line is the positive, the short line is the negative. And this is electrical current flow. And so once you know that this is the positive and this is the negative, that's the starting for this. If you want to think of it as a maze or a labyrinth, the current's going to flow from the positive. That means that it's going to flow upwards in the foreground, and you would trace it out like you were tracing a maze. You know those children's mazes that you get when you go to a Denny's or something like that? It's like this crummy little maze where it takes you 10 seconds, and then you're like, okay, where's my pancakes? Then you have all these current pathways mapped out, and then you can take your hand and wrap your fingers around, right hand rule-wise, and it'll tell you the polarity. I know that a lot of this drawing was already done for us. All right, so a solenoid's strength is determined by three factors. One is the amount of current flowing through. Two is the number of loops. Really, it's the number of loops the coil makes per unit length. Because remember, if I've got the same number of loops over a short length as over a long length, it's not going to be the same, right? So it's per unit length, really. And then a third property is called the magnetic permeability of the core, which sounds like fancy talk. I guess it is. But what it really means for us is how well a magnetic field forms in the material. And so for all of our homework problems, we're assuming that the core is a vacuum. Magnetic permeability for vacuum is a constant value. Magnetic permeability for iron, as opposed to aluminum, as opposed to some doped alloy, they're all going to be different, right? So usually for high school and right up into even secondary university, they'll often just say, okay, well, it's just a vacuum inside, just as people get used to the ideas. Okay, so for us, we're all cool with it just being a vacuum. I'm not going to deal with different permeabilities. Anyway, in electromagnetism, permeability is the measure of the resistance of a material against the formation of a magnetic field. Hence, it's the degree of magnetization that a material obtains in response to an applied magnetic field, and the domains of a core may reinforce the strength of the solenoid. That guy just got stolen straight from, I don't know, probably Wikipedia or something. I really should reference these things. But the short answer is how well a magnetic field forms in a material. Okay. Now, as a side note, it turns out that your car, if you ever drive over top of a traffic light, or if you drive near a traffic light, at an intersection, your car becomes a part of the core. So if you ever look at a traffic stop, there are like these big pavement patches. Usually they're like a rectangle or something, right near where the white line is where you're supposed to stop. And if you were to dig that up, what you would find is a great big solenoid that's about the size of a hula hoop. And if you drive over top of it, effectively, here's the solenoid. And there's, low current always flowing through this thing. But if you put your car over top of that solenoid, your car effectively becomes a core that's not quite inside, but it's right over top of it. And what this solenoid tries to do is it tries to align the domains of the metal in your car. Now that takes work. And because it takes work, isn't that going to change the resistance in this wire? And if the resistance of this wire increases, then that triggers something. Let's just call this the happy little computer. It triggers the happy little computer, our friend that runs the traffic light, because the resistance has now changed because you introduced a core with domains that are trying to get aligned. Now that computer knows that somebody's there. And then that causes the light to get triggered, right? So if you try to drive over top of one of these patches and you were just driving a purely plastic car, would it work? No. If we do decide to build purely plastic cars, we get rid of the big heavy metal engines and all that sort of thing, what are we going to have to do to get around this? Because all the traffic lights use this right now, all of them. What are we going to have to do? By the way, the nice thing about these coils is that there's no moving parts. So they last a long time, like decades. Fantastic. But what would we do if we didn't have iron cars? We got one suggestion? Yeah?
Throw in a pressure plate or something instead.
Ooh, I like a pressure plate. Who doesn't like a good pressure plate? Yeah, that's probably a good one too. You're right. We could probably have like something that flexes ever so slightly, and that little flex is going to cause a current induction. That could be a thing. I get people say we could put cameras. The pressure plate's probably a better thing because the pressure plate's probably going to have better long-lasting durability underneath the pavement, right? As opposed to a camera, which you have to wonder, is it going to get covered by ice in the winter, rain in the summer? Is the bird going to poop on it? Like all that sort of stuff, right? So having these things that are durable, this is a really good model moving forward. And we'll have to think about what we're going to do if our cars become less metal, if they become less magnetic, if there's less domains inside of them to align. Cool? Honestly, I always think it's so cool, all these different civil engineering things and city maintenance things that just run invisible in the background. That's one of those things that's invisible in the background, and if we didn't have it, the traffic lights wouldn't work properly.